So, this is the lecture number 15 of module 10. So, where we are basically discussing thermoelasticity. So, in the last class we have introduced what is the use of thermoelasticity, and basically the Fourier law of heat conduction we have discussed. And then after Fourier law of heat conduction, then we actually described the conductivity of a material, and then heat propagation or the heat equation for one dimension also we have discussed. So, in this lecture we will introduce the basic Duhamel Newman equation, and this equation is actually connected with the how total strain is related to the mechanical strain as well as the thermal strain. Now, the basic assumption for here is heat conduction through elastic process is not affected by the deformation of the solids. So, this is an assumption, even though this is valid for the structural material that we are using. So, it may not be valid for all material. So, the material we are talking here is mostly follows this, and if this assumption is taken care, or if this assumption is taken, then the total strain of a elastic body is essentially mechanical strain and thermal strain. So, mechanical strain which is due to the external loading, and then thermal strain is due to the temperature effect or increase or decrease of temperature temperature change with the surrounding. So, that we know that epsilon ij is the total strain. So, it has two components, epsilon m and epsilon ij, and then epsilon thermal, the thermal strain is essentially alpha ij into delta T, which is the T0 is the temperature at the surrounding, and delta T is the increment of temperature in the body, and T is the final temperature. So, now this relation is specifically known as the Duhamel Newman equation, and this alpha ij is the coefficient of thermal expansion, which all of us know that from our knowledge of mechanics, basic mechanics or the first year mechanics, we know what this expansion of thermal expansion coefficient of solid means. So, now we will derive this Duhamel-Newman equation, and to do that actually we need to have some understanding of the usual strain energy function and how we can derive that. So, for instance, the if you remember the Hooke's law, then this strain energy function is a function of strain only, the epsilon. So, now this we know from the our previous elastic deformation, only elastic deformation case, where strain energy function u is dependent on the strain only. So, now if I expand this strain energy in terms of Taylor series, then what it looks like, this strain energy is, if I can write or if I can expand it Taylor series, so which is u0 plus u0 or del u0 del x, that is del epsilon ij into epsilon ij plus del squared u0 into del epsilon ij del epsilon kl into epsilon ij epsilon kl and then half. So, then the third order derivative and so on. So, this is a Taylor series. So, this is the first constant term and then this constant term becomes first derivative of this thing and then epsilon ij, and then half of this half is coming due to the factorial and then epsilon ij epsilon kl. Now, if I now write this as this u0 is my constant, and then this del u0 del epsilon ij, I write c ij, right, epsilon ij, then half of c ij kl, that also we know, and then epsilon ij epsilon kl, and then this becomes this. Now, the stress strain relation for three dimensional body for following the Hookean material or the linear elastic body, that also we know that sigma equals to c colon epsilon, or in a initial form sigma ij equals to c ij kl into epsilon kl. Now, how sigma ij is defined? Sigma ij is essentially sigma is del this strain energy by del epsilon. So, if I now take the derivative of this expression, so del u by del epsilon, if I now take, so this quantity goes off. So, and this becomes c ij plus this is a quadratic function. So, and the derivative will be c ij kl into epsilon kl. So, now this half will cancel the derivative and then so on. So, now if I neglect the higher order terms or the third order tensors or mixed form of tensors, means the term after this, then this is essentially my Hooke's law, that is sigma ij equals to c ij plus c ij kl into epsilon kl. Now, this is essentially the pre-stress or predefined stress that we may or may not consider the pre-stress. So, if the body does not have the pre-stress, then this is my this quantity C I j becomes 0. Now, if C I j is 0, that is pre-stress is 0, then my constitutive equation is essentially sigma I j is C I j K L epsilon K L. So, this is my original Hooke's law that I have derived from the Taylor series expansion of the strain energy. Now, using this thing, actually I will using this thing I will derive the strain energy for the thermoelastic material. Now, if I now consider a thermoelastic material where the strain energy function is not only dependent on strain, but also dependent on the strain energy, the temperature. So, U is not dependent on strain, it is dependent on the temperature also. So, now then if I expand this thing U0, it will be function of temperature, and then I first expand in terms of strain, or it's the Taylor series I am first writing in terms of strain. So, again this del u by del epsilon I j, then epsilon I j, then del epsilon half of del squared u0 del epsilon I j del epsilon k l, and then epsilon I j epsilon k l, and so on. right. Now, you see this u0 is a function of temperature only. So, what I did is here first we expand in terms of Taylor series with respect to only strain. Now, you see for each parameter, each term is temperature dependent term. So, first let me write it in this way, that u0 is a function of temperature, then this is Cij, it is also a function of temperature, and then epsilon ij is my strain, and then half of Cij KL, it is also a function of temperature, epsilon ij and epsilon KL, and so on. Now, again if I expand this thing in terms of temperature, for instance Cij. So, Cij I am expanding it again in terms of Taylor series with respect to a temperature T0. So, the temperature change is now delta T is actually T minus T0. So, T0 with respect to T0, if I can expand now, so which is this Cij at T0 plus delta T delta Cij of T0 delta Cij of T0 with respect to T into T minus T0, and then so on. This is the first term epsilon ij. Now, similarly the second term plus half this term I have to expand, this term I have to now expand. So, this term and this term actually I am expanding in terms of temperature. Now, to do that Cij KL T0, it is a function of T0, then del Cij KL of T0 into del T into T minus T0, and then again second order terms. So, this multiplied by epsilon ij epsilon KL, and then again all other third order terms. Right. Now, if I now use my original definition of stress, that is sigma is the first derivative of the strain energy function, which is sigma ij is del psi by del epsilon ij. If I now use this definition for an hyperelastic body, but now here my psi or my psi is my strain energy here, which is here I am representing in terms of u. So, del u is my epsilon comma t. So, it is a function of temperature as well. So, now if I now take the derivative of this expression with respect to epsilon ij, then del epsilon del u by del epsilon ij is my, this term goes cancels out, and this term only this c of ij T0 plus del c ij del t into t minus T0, then other terms other terms will be here, and then from here again the this is a quadratic function. So, half will be absorbed in the derivative. So, the first term will be Cij KL, it is a function of T0 plus this, then the second term del Cij KL by del T into T minus T0, and then but this will be with epsilon ij, right. Now, and then the other terms as well. So now here if we neglect, if we consider the small deformation assumption, and then if I consider that del t is less than comparatively less than T0, then I can neglect the higher order terms in this Taylor series expansion, and basically I can write this the sigma ij which is coming from here. So, sigma ij is my Cij T0 plus del Cij by del t into t minus T0, and then Cij Kl of T0, and this is also I am neglecting. So, now here this I can say approximately equal for small deformation. Now, this is very similar to the pre-stress of the previous case. So, if I take this Cij is 0 pre-stress, then my this will be epsilon Kl. So, this will be epsilon Kl. So, now if I consider the pre-stress term is 0, that is Cij is, if I take 0 here, then my stress strain relation for the thermoelastic material is Cij Kl epsilon Kl plus this quantity. Now, del Cij by del t into t minus T0. Now, this quantity, if I say this quantity is my beta ij, or specifically the minus beta ij. So, Cij Kl epsilon Kl is minus beta ij t minus T0. So, this is my the thermal stress actually, and this is my the total stress. So, this is essentially coming from the this is known as the Duhamel Newman equation. Now, Duhamel Newman equation of this form. Now, once we know this form, then we can easily convert it to the other means that we can write the stress strain in terms of thermal and the mechanical strain. So, now if I write similarly the compliance relation, so where I write epsilon ij in terms of sigma ij, which is essentially 1 by E into 1 plus nu into your sigma ij minus nu sigma kk delta ij, then this if I substitute here, what we get is something like this, that we will see now. So, now here what I have written is your this quantity. So, now here what I have written is this quantity. So, here this quantity is essentially coming from the Duhamel Newman equation. Now, if I write this sigma in a matrix format, if I write sigma is essentially C into epsilon, here C I am writing in a void notation, and then this beta I can write it in a matrix form also. I can write beta or the beta matrix beta and then t minus T0. So, if I now write C inverse sigma is essentially epsilon minus C inverse beta t minus T0. Now, this quantity I am saying alpha matrix is the coefficient of thermal expansion of solid. Now, this coefficient actually then if I write this is my total strain and this is my thermal strain. So, and this is equals to the mechanical strain, which is this quantity. So, now this actually proves my mechanical strain plus thermal strain is my total strain. So, now how this alpha is derived, that also is clear. So, C inverse beta if I write, which is a alpha. Now, for an isotropic material, alpha ij, this quantity is constant, which is alpha delta ij. So, that means the three direction it is alpha, that is x direction coefficient of thermal expansion of solid is alpha, y direction is also alpha, and z direction it is also alpha. Now, this thing it can be for an anisotropic material also alpha 1 in the one direction or x direction, alpha 2 in the y direction, alpha 3 in the z direction. This can happen, but so this if I write it in a stress strain relation, the stress strain relation becomes now this sigma is becoming C into epsilon minus alpha into T minus T0, which is essentially delta T. So, alpha delta T. So, this is my final constitutive relation for the solids. So, you see this total strain, epsilon is the total strain here, this is the total strain, and alpha delta T is my thermal strain. So, this quantity is essentially the elastic strain, so or the mechanical strain. Now, for an isotropic material, this can be easily observed. This can be easily observed. So, for instance, here we can see this isotropic material, which is alpha into delta, the thermal strain is alpha and delta ij. So, this is delta T, and so I can write the compliance relation, that is strain versus stress relation, and then from here actually we can get the compliance relation for the thermoelastic material. This is for the mechanical part or the elastic part, because we are essentially considering elastic material. So, this is the elastic part of the strain, and this is the mechanical total strain, which is composed of mechanical strain plus thermal strain. So, now this is the basic introduction of the Duhamel Newman relationship of the thermoelastic material. Now, if we can modify this. So, this is with this. So, if I substitute ijk with in the previous relation or this relation. So, epsilon kk, I can get the expression for epsilon kk, which is this, and then if I want to find out sigma kk, so I transfer it. So, once I transfer it, it looks like in this form. Then epsilon ij also I can do it, and I can after some manipulation I can convert it to the first Lamé constant and second Lamé constant. This I think already we have seen, that is mu and lambda, that mu is the first Lamé constant and mu is the shear modulus of the second Lamé constant. Now, once this is done, then Duhamel-Newman relation for isotropic constitutive material or isotropic material is this. So, this is the compliance relation and this is the constitutive relation. The constitutive relation, you see in the thermal strain part, there is a 3 lambda plus 2 mu, because this is how it has been derived. So, because this quantity is essentially the beta that we are discussing in the previous slide, and this is alpha is the thermal coefficient, thermal expansion coefficient. Now, this is the for the isotropic. So, this can be modified for the anisotropic material as well. Now, if I now consider the basic energy conservation equation, that is for a body with thermoelastic energy is required. So, first starting point is the first law of thermodynamics. So, all of you must have studied the first law of thermodynamics, which is the in a basic elementary notation we will follow here, and which is the ddt, time derivative of kinetic energy, and the internal energy is equals to work done plus the heat flux Q. So, this or heat energy capital Q. So, now if the kinetic energy I know, if I consider a body here, this body, and this body is suppose d omega is the boundary and omega is the body, and then there is a normal here, this normal, and there is a heat flux is also there. So, now in a purely elastic place you do not have small q. So, there is a heat conduction is happening. So, there is a q here, and this body is with the mechanical loading, some mechanical loading is there, and there is a heat conduction is also happening. So, now this if I write the expression of the kinetic energy, which is we know half of mv squared. So, which is m is essentially we are considering the mass density rho. So, this is my kinetic energy, and this is my the internal energy rho into internal energy density, small epsilon is here internal energy density. So, this is integrated over the total volume. So, this is my internal energy density, and this is my the work done. Work done is due to, there could be a two force, there is a traction force here, maybe there is a traction force here. So, which is this traction we know that sigma dot n is T. So, this sigma I j n j into V is my total external work done due to the purely mechanical loading, and then this is my the volume volumetric force due to the body force term. And then the heat energy is essentially this we have seen from the previous lecture, that q n I is the heat flux in the boundary. So, and rho h is the source term, any prescribed source term within the body or not. It may be h may be 0, h may not be 0. So, if there is a heat source, then there is a heat energy inside the body. So, which is over the omega or the capital omega inside the body. Now, if I substitute these quantities here, so this looks like this. Now, if this will now this will now see how this looks in a system. So, in a if I now do this operation and using the divergence theorem, I can change this to the volume, that means the body. So, divergence theorem we have studied earlier, which actually converts the surface integral to a line integral, or the line integral to a surface integral, and a volume integral to a surface integral. So, here what we are doing is a surface integral, actually we are converting into a volume integral. So, now this if I use the divergence theorem here, and similarly the divergence theorem if I use here, so I can compute the volume integral. So, this is the expression for volume integral, this all of you know. And now, after some manipulation, I just take the time derivative here. So, if I just take the time derivative, so it will, one of them will appear v dot, and since there is a half, so that will absorb, and then the internal energy density will be time derivative. So, this if I after some rearrangement I just form this. So, if you look carefully, this first term is essentially this quantity we have already seen. So, this is the equilibrium equation that we have observed. So, this is nothing but the sigma divergence of sigma plus F is the body force equals to rho u dot or u double dot, or if u is the displacement, then acceleration. So, since v is a velocity, so it is v dot. So, this is essentially your equilibrium equation or the force balance. So, this equation we have seen, we have put 0 for a static case here. Now, this is since we are considering for general dynamical case. So, this will be the inertia term will be there. So, now this equation is essentially 0. So, this becomes 0. So, now what is left is essentially this quantity. Now, so this quantity first term is 0 because it represents the equilibrium equation, and then the second term is essentially this quantity. So, after some modification I can just now write this quantity, that is internal energy derivative with respect to other quantities. So, you see the first term is due to the your stress, and then this is due to the heat flux, and this is the source term. So, now if I little bit modify this, this is the final expression, and now we have the Fourier law of heat conduction, which also we know, which is for an isotropic material heat flux Qi is k into T comma I for an isotropic material. So, now this Duhamel Newman relation we have studied just previously, and from the basic thermodynamical theory where considering the ideal gas approximation, we can have this epsilon dot equals to C is the specific heat, is the temperature derivative with respect to time. Now, if I just write it little for its stress free condition, what does this stress free condition means? That means there is no sigma ij, this term is not there. So, now this term is there, but there is no mechanical strain. So, only the thermal strain part will be there. So, which is coming from the Duhamel integration. If you look from the previous case, this term, this part will be 0. So, this part will be there. So, there is no mechanical strain part. So, now then this is coming from the heat conduction equation, that is Fourier law. Fourier, this is k is the coefficient of conductivity, and then rho h is the source term. Now, if I after some rearrangement, if you see this, there is a couple term here, and this is coming this. So, where the alpha and epsilon strains, even though there is a in the stress free condition, there is a strain which is coupled with the coefficient of thermal expansion coefficient. Now, here is the departure for our theory. What is that departure? Is that we want to study the uncoupled thermoelasticity here. Now, here this coupling is actually creating a coupled form of the thermoelastic equation. Now, for a uncoupled system, this quantity must go. So, now this if this term becomes 0, then we get the usual uncoupled elasticity. Now, it is if there is a no source term inside the body, then this is the energy equation or the stress state. So, this is this epsilon is actually the rate of internal energy, which is essentially C T dot from the basic thermodynamical theory, and then this becomes my final energy conservation equation. Now, so in a general uncoupled formulation, what are those things? The things are strain displacement relations are these, which is usual that we know from the elastic deformation theory. Strain compatibility equation, which is also we have studied earlier. Equilibrium equation for a static case, this is the equilibrium equation, and for here comes the speciality of thermoelastic constitutive relation. You see this this quantity is due to the mechanical this thing. So, this will be epsilon kk. So, and this part will be due to the thermal stress part. Now, the energy equation, if there is a no source term, so if H equals to 0, which also we have derived for a uncoupled form, what will be the energy equation. So, as a whole we have 3 displacement unknowns, 6 strain components and 6 stress components and the temperature unknown. So, total in a elasticity case there is another unknown which is coming as temperature. Now, for an uncoupled thermoelasticity, temperature will be generally given to you, because you are not actually solving the heat conduction equation, or if you solve the heat conduction equation, that means the thermoelastic or the Navier's equation of elasticity actually you solve separately, and heat conduction equation or the heat equation you solve this separately. From the heat equation you get the T, that is a temperature distribution of the body, and once you plug into this T into the Duhamel-Newman constitutive relation, which is delta T, which can be space dependent, that means which the xy variation can be accommodated here. So, this T once you get it from the heat equation, you can have the usual elastic problems, usual elasticity problem, but thermal strain as an additional strain there. So, now this as a total you have 16 unknown, where in the elasticity case you have total 15 unknown. So, temperature unknown was not there. Now, in case of A, it is important to remember here in the coupled thermoelasticity case, you solve both the equation, thermal heat equation to find out the temperature, as well as the displacement, thermoelastic displacement. You solve both equation together to get the distribution of displacement and temperature. But in case of uncoupled elasticity, you solve sequentially, or you get the temperature distribution, or that means the temperature. Our first assumption in the beginning of the slide we have discussed that heat conduction doesn't change the properties of the material, or doesn't affect the response of the material. So, if we follow this thing, then this term basically gives us the uncoupled elasticity, uncoupled thermoelasticity. So, finally, this becomes a 15 unknowns for the elasticity and 1 temperature unknown. So, generally this temperature will be given to you, and otherwise you can solve heat equation in a body to get the temperature profile in a body. So, once you are done with that, then you solve the usual thermoelastic problem where temperature is an input to the system, and then you get the thermoelastic response in terms of stresses, strain and displacement, which is usual as per the our previous discussion. So, I stop here. So, we will continue in the next class, where we will discuss some of the specific cases for plane stress, plane strain thermoelasticity. Thank you.